Welcome. This video is a continuation. Those of you in my course should have already watched these previous two videos. In this video, we're going to make a sketch of y equals g of x, then explain what this graph means within the context of this question. Before we can do that, we need a table of values. So please go back to part A and fill in a table of values similar to mine on your own paper. Now, of course, your paper might be organized really differently, so I'm guessing you've already filled up all the space with part A and then part B. So you might be on a blank sheet or at the very bottom of the page. Just make sure, if you're in my class especially, that you don't squeeze this last part into a corner of your paper. If you're out of paper, just get a blank sheet. Remember, I do look at your notes and I will look at that. Do not just squeeze this into a corner, please. All right, as you can see, I have my table. Now I want to go ahead and make a graph. And so this is the point where you want to get a ruler out. And really, I insist, please get a ruler out. Don't just wing it. And let's see, I'm going to go from -1 to a little bit above -7. And my y-axis, let me see, can I draw a dot there? There, kind of. So let me move my ruler. It might be easier on a paper. There we go. That's where my y-axis is going to be. And I'm going to mark all these spots. Remember, math is accurate, so please keep your graphs, fairly accurate. All right, now let's rotate our ruler and go ahead. If you can do this without following along, please just go ahead and make your own graph. All right, I'm partially there with setting up my graph. As you can see, I moved it to a new spot because it was not going to fit. And let me make sure my scale is done accurately. That's why I used a ruler to measure these and know that the distance is actually equal between each of these marks, and the same thing here. Those of you in my course, you will always lose points for not accurately scaling and then labeling your graph. So what I mean by labels, what it sounds like, make some labels. So that's 4, 1, 2, 3, 4, here's 5, and I guess I can go to 7 here and 9 just to make it clear. And really, if you want to, that's -1. And here we have x, and we have y equals g of x. So first, a really big point. Whenever we're going to graph an antiderivative, if we don't have some initial condition, then we really can just draw this shape. We are not going to know exactly where it is vertically. We're not going to know where this graph is vertically because that initial condition is going to shift the graph upwards or downwards. Luckily, if you recall, our initial integral, that is, g of -1, well, that's equal to the integral from -1 to -1 of f of x dx, which is just 0. So this is our initial condition here. All right, so at -1, we have 0. And now we can add to that. So at 0, we're going to go down 1/2. And honestly, it makes this graphing so much easier. So at 0, I'm going to go down -1/2. At 1, we're back again to 0. Now beyond this, I'm going to use a ruler just to be a bit more accurate. And since I use the same scale as the labels on my ruler, I can go up vertically to 1.5 here. 1.5. There's 1, here's 1.5. And I know that at this 2 mark, the x, or the input of 2, gives 1.5, so I can draw a dot there. So for this next one, I'm going to go vertically up to 3.25. That's 1, 2, 3, and this would be about half, so let's go down to 1/4. So 3, we have 3.25 there. Okay, let's keep going. At 4, x equals 4, we have an output of 4.5, which would be up here. And let me go ahead and find that. At the input of 5, so that's this one, we have an output of 5.5 about there. So let's use the ruler. Those of you in my class, I really do expect this level of detail with a ruler. Now at 6, we go up to 7. So there's 5, 6, 7. And that's the mark, we'll make it 6. And then at 7, we'll go ahead and mark up to 9. All right, so let's go ahead and now connect these dots. I'm going to emphasize each of them a bit more. All right, so here is our function g of x. It's pretty steady rate at which the water is increasing, except for a couple spots there. Now I want to see our graph of f on top of this, so bear with me while I move things around a little. Okay, there, so we can see the graph of f here. And what's really nice is we can kind of match these up. We can see the minimum, the extreme point of g, matches up with its derivative. Remember, this is the graph of y equals g prime of x. That's what f of t is, this integral. This is y equals g of x here. And so when g has a minimum, this goes, that is, its derivative goes from negative to positive. And then here you can see that the slope from 5 to 7 is steep. It's actually steeper than about here, which was pretty steady. And then here was slowing down. It was still positive, it was just less positive is the idea. This is a less positive rate of change between, say, 2 and 4. And then between 5 and 7. And we can confirm that because look, this line here looks steeper than this line here. So more steep. This is less steep. But they're both positive, and if you notice, this is here versus here. This is this slope here is not as positive as this slope. Now finally, what can we actually say within the context of this problem? So remember, this graph here, that is the graph of f, gives us the amount of water accumulated when we figure out that area. What this graph here is telling you is really the height of the water in the tank. And I don't remember what I said in my original units where I just said a gallon. So actually not height, it's the volume of the water. So this is water in gallons. So water in tank in gallons. And this is hours since midnight. Whereas this other function is still hours since midnight, but the height is the rate at which the water is either entering or leaving the tank. So rate of change, rate of water change. Okay, so I hope you found this helpful. Remember that whenever our derivative here is flat, that tells us that the slope here is at the slope here. Where is that? Between 4 and 5? It's not necessarily flat, just increasing slower than, say, here. See how much it's increasing here versus here? And of course, whenever this has a really steep slope, that means we know the volume in the water, the number of gallons, is going to change pretty quickly. Okay, please keep calm and math on.